Today is 24th. The question is setting the boundaries in a polar plot in Mathematica. So, define your function. R of theta, say, equals something or other.
Is that an I or an R?
That's an R. This dot is, I don't know where it came from. No, I made it by mistake. R of theta is equal to 2 sine theta. Okay. That would be defining your function R of theta. If you want to plot this, you do a polar plot. And you want theta to go from 0 to pi would trace the whole thing out. That's all you really need. 0 to pi.
Okay. I tried that, but didn't.
Do it exactly like that. Go ahead. You got it right there? Go ahead. Let's see. And do it and see, and we'll fix it up. Common mistakes here are the sign not being capitalized, argument of sign not being enclosed in square brackets. Those are common mistakes. Still.
There was a poster behind your chess table in
There-
your office
There's a poster behind, yeah.
that has a quote on it. It's by this guy named like Joseph Sylvester or something.
So that's, yes.
Who's that?
He is a mathematician in the, I believe, 1800s. And he said something about number theory being like the queen of something. It was an interesting quote. It was a mathematician. I believe he's late 1800s, although I'm not positive. Not one I'm really familiar with that much.
Is he like a great mathematician? Or?
Yeah.
Was he better than you?
No, he wasn't that good.
Oh, okay.
No,
It's
he's
working.
Is it working?
Yeah. I guess
All right. Good deal. Liam.
My lab, I feel like I got kind of wordy with my conclusion. Are we gonna get like faulted if I don't know how to summarize my conclusion should be.
Well,
I got more complicated as I started explaining it.
yeah. It's easy to get too complicated in that lab with the A, B, and C if you're going to vary all of them. Then things are just kind of crazy. No, you won't get faulted for that. Basically, the idea is you do a decent job with the explanations, you're going to get probably a 92 or so.
All right.
Okay. If you do, almost nothing, it's going to be a 90. But at least you got the lab there and you did something. If you do a little bit more than that and do an explanation, you get a 92. To get beyond that, you're going to have to take. There are some cool ones already, though. I mean, some were already cool, right? Yours was pretty cool, right? Yeah, I think yours was pretty cool. Yeah. Huh? Yeah.
It was like a hill.
Yeah, it was pretty neat. Yeah. To go beyond is a little bit difficult, but it can be done. If you do some maybe additional plot or so, use manipulate and do that with some kind of explanation. The labs, as you know, are going to go from 90 to really the best. It's going to be like the best grade you're going to get in a lab is whatever Dan gets. So the bottom line is 90 to 95, 96 would be an amazing lab. I'm very concerned about grade inflation now with giving a grade that, I gotta tell you, sometimes when I give a grade to someone, it's what it should be, in black and white, but in my heart, I know that person shouldn't be getting that grade. You know what I mean?
Yeah.
So I don't want the labs, high grades on labs, to pull somebody's grade up to an extent where they're getting an A in this course, and I don't think they're an A student. So 90 to 95 doesn't hurt your A, but it doesn't really pull your tests up. So, Liam, I'm sure whatever you do is going to be 92, 93.
I just don't want you fuming as you're sitting there belting
don't
through
even
my
worry.
paragraph or
Someone
whatever.
does better than Dan. Does he get an auto 100?
Oh, better than Dan. You are talking.
Then
What do we gotta do to get
Hiring
on?
some PhD
Nothing.
students.
Would we have to like? I
You
think
won't
you'd
get
have to get a
Like
major.
break for
Like
a
get
break.
a major.
It'll work.
I have not given it out a 99 ever because of what I just said. It's a grade inflation kind of a thing, and 99s would contribute to that. 95, it seems to me if you get 94 or 95, you were doing awesome on the labs. And that is pretty significant, because that'll take a test that you can get no 90s on any test, or in your final, get high 80s and stuff, and with that 95 average in the lab, just be enough to put you in that A range. And I'm not really sure I like that, but it can be done. Sorry, just 90 to 90.
What if it's like a lab that you would consider to yourself in your heart a 99?
I would give you the 99, but there's no lab in my heart that would say 99. Because I remember some of the labs, I've had students come through here, and they've done labs that would just blow you away. I had one student, I'll tell you, that's all he did was mathematical labs. He failed all his courses. That's what he did. I swear, that's what he did. And he did labs that were unbelievable. What's that?
You really only did mathematics.
Very little else, because I think he failed everything else. And he didn't even do well on the test either, but he did amazing mathematical labs. Actually, I think what happened to him, though, is he ended up going to UMass and doing some kind of Mathematica stuff, and was fine. I mean, had a good job doing Mathematica stuff, some kind of modeling thing for somebody, and it worked out well. But anyhow, it was weird stuff. All right, we got any other questions? All right. I remember him, so he's interesting. Okay, we're going to do a couple proofs today, just because there are some times in the Calc 3 where we have to prove things. And the first thing we're going to do, is talk about I and J. I don't think I mentioned I and J yesterday, so let's take a look at this. I did mention unit vectors, but there's two special unit vectors that you should be aware of. And one is I, and it's a unit vector, it gets a little hat. Well,
You can't escape it.
I know.
what's that? No?
Utopia natural, but it's close.
Oh. And J, which is 0, 1. All vectors in the plane can be expressed in terms of I and J. For example, if you have the vector 5, 2, this vector could be expressed this way. This is component form. This is the usual, okay? But it could be expressed this way. And Course Compass does this quite often. They'll express this vector this way as 5i, okay, plus 2j. Okay. What does 5i mean? It means 5 times the vector, 1, 0. 2j would be 2 times the vector, 0, 1. This is a scalar multiplication where you multiply through by the constant. And then you can add up the components when you add vectors to get the vector 5, 2. Okay? I personally prefer this notation, and I'm going to use this all the time. But Webenstein does use this notation a lot. Okay, so be aware of that. Okay, a couple things we have to do. One thing we have to do today is define another operation. Another operation is the dot product. The dot product of two vectors, let's say u is equal to u1, u2. And let's take vector v to be v1, v2. Their dot product is equal to u1, v1 plus u2, v2. It's a scalar quantity. It's a real number. Okay, it's not a vector. There's another vector operation of multiplication when we get to 3 space, probably tomorrow, where you take the cross product of the two vectors, and the result of that cross product is yet again another vector. Okay, but you don't have a cross product for vectors in 2 space. So dot product is equal to the sum of these two products. It's a real number. What do we use the dot product for? Well, one very important result of the dot product is to find the cosine of the angle between two vectors. And that's what I'm going to prove right now. Okay. So, did you guys do this in physics? Did you do the proof?
Yep.
Today,
Oh, you did the whole proof of law of cosines? Oh.
You did,
No, you didn't do it as a law of cosines?
he just gave us.
He just gave you the result?
The two definitions of the dot product, and then we set them equal to each other and use them.
That's pretty cool. Well, that's the definition. There's really only one definition. Physics people. All right, but anyhow, what we're going to do, here's what we're going to do. We're going to do the proof. Yeah, I'll prove it. We'll do the proof. Yeah. Here we go. Let's take two vectors, u and v. And v. And what we want to do here is find the cosine of the angle between the two vectors. Okay, that's what we want to do. Let's complete this triangle here. Let's draw this. And this vector is going to be, what vector is this here? Yeah, that's the minus, u minus v. Okay, so here's what we have. Watch this. I'm going to call this A, call this B, call this C. We have a law of cosines here. C squared is equal to A squared plus B squared minus 2AB cosine theta. That's the law of cosines. Okay? What we're going to do is solve for the cosine of theta. Let's see what happens. It's going to be a little bit involved. It gets a little messy, but turns out to be fine in the end. C is the length of this vector. C is the magnitude of this vector, u minus v. C squared will square that. Okay. A is the magnitude of u. We're going to square that. B is the magnitude of v. We're going to square that. 2a b cosine c, which is what we're looking for. Okay? With me? Okay? You're not going to be responsible for this proof at all. It's only the end results that we're going to need. But I do think it's incumbent upon me to prove some of these results rather than just give them to you. So, u minus v. How do you subtract the two vectors? Well, you subtract the respective components. U minus v will give us this. And that's equal to magnitude of u squared plus magnitude of v squared minus twice the product. I'm going to keep these guys where they are. And cosine theta is what we're looking for. Okay, here we go. Magnitude of this vector is the square root of the sum of the squares of their respective components, just what we have here. And we're going to square this. It looks bleak. Mr. Shang, how you doing? It's not Mr. Shang anyways. It's Shang. Mr. Chung. Okay, square this guy, square this guy, square this, square that, twice the product. Okay, whoa, this looks really bleak. Well, let's do it. We started it, we're going to continue. When you square the square root, you eliminate the square root. So I have u1 squared
minus 2u1 v1 plus v1 squared plus u2 squared minus 2u2 v2 plus v2 squared. That's equal to u1 squared plus u2 squared plus v1 squared plus v2 squared minus twice the product. Holy mackerel, is this a mistake or what?
Why, Burns?
I know, that's a good question. Why?
Actually, more like U or V. We gotta make these right here.
All right. What can I do here to both sides of this thing? I can cancel some things. What can I cancel? U1 squares. What else? V1 squares. What else? U2 squares. V2 squares. Whoa, that's not bad. What else I got here? I have a negative 2. I can divide by negative 2 as well. I'm going to end up with U1 V1 plus U2 V2 when I take out a negative 2 equals, take out that negative 2, U V cosine theta. Okay? I'm looking for the cosine of theta. The cosine of theta, therefore, is equal to U1 V1 plus U2 V2 divided by magnitude of U, magnitude of V. But what the heck is U1 V1 plus U2 V2 equal to? What is it? It's equal to? What is that equal to? Yeah, the dot product. There it is. That's the definition of the dot product.
Wow.
So we get U dot V over the product of the magnitudes. Voila. I'm going to put a QED on this.
Yeah, we didn't do that mechanics.
You didn't do this?
And we skipped to the second to last step.
Oh, you call this a definition.
Oh, they call it cosine times magnitude of u times magnitude of v as a definition.
Yeah, that's not a definition.
Wow, she did.
Wait, who is this?
Shank.
Okay.
Oh, okay. I don't want to say anything bad about her. Okay. I don't mind saying something bad about the other guy, but all right. But she teaches math classes too, and she's a really nice person. All right. So anyhow,
I think it's for time's sake.
what's that?
I think it's for time's sake.
Yeah. All right. Probably. Okay. Here we go. I will speak to her though. All right, but so cosine of an angle between two vectors, dot product over the product of the magnitudes. This is very useful because there are times when we want to know if two vectors are perpendicular or orthogonal to each other, okay, perpendicular to each other. And to do that, what must be true? Well, the cosine must be equal to what if these two vectors are going to be perpendicular to each other? Zero. Okay, cosine must be 0. That means the dot product is equal to 0. If the dot product is 0, the cosine is equal to 0, and the angle is 90 degrees. Cosine, okay, 0. All right, cosine of 0 is equal to, all right, 1. Cosine of 90 degrees is equal to 0. That's really what I wanted to say. Let's take an example. Let's take an example of two vectors. Let's find the angle between them. Let's say we have, let's take the vector 5, 1. And let's take another vector 1, negative 5. What about the angle between these two vectors? Well, you say the cosine of theta is equal to their dot product over the product of the magnitudes. That's what we just derived. We proved that. Okay. The dot product is 5 plus negative 5 is 0. It doesn't matter what the magnitudes are. Okay. We get 0. And if the cosine of the angle is 0, the angle is 90 degrees. Okay? Cosine of 90, pi over 2 is equal to 0. Are you okay with this? Wait, somebody's not okay. You're not okay with this, are you? You okay with this?
Just a little.
All right, what's wrong? Talk to me.
Why did you put the 5 and the 5 together?
Why did I do what?
Why did you put the 5 and the 5 together?
I did their dot product, which is 5 times 1 plus 1 times negative 5. That's their dot product. That's how you find the dot product, which is equal to 0. Okay? Are you all set on this? Okay? That's going to be really useful. But there's other applications to this, and that's another proof we're going to do right now. Okay? The other proof we're going to do is to find a projection of one vector on another. Now, what did she do about the projection of one vector on another? Did she derive it?
Yeah, I think so.
Okay, well, I'm going to do it, and we'll see if we agree here. All right, let's take a look. Let's take vector v, say, and another vector u. The projection of u on v, okay, that's what we're going to write, that's the projection of u on v, is this. If we drop a perpendicular from the terminal point of u onto v, this vector is the projection of u on v. And that's going to be extremely useful, okay? One thing we're going to want to do is when we talk about vector-valued functions and we have an acceleration, we want to find how much of acceleration is directed along the tangent to the curve, the path of motion, and how much acceleration is directed along the normal line. If you're going to design a course, a race track at Daytona, you've got to figure out a banking here, and that banking formula involves the projection of these vectors, the acceleration vector on the tangent and normal to the curve. Okay, it's kind of a cool calculation. You need friction forces and all kinds of things. There's really interesting math. But anyhow, what's that?
It's all just so Ricky Bobby can race.
Oh, I don't follow that. I have a son-in-law that's big on NASCAR stuff.
That's Talladega Nights.
That's a movie.
That's just Will Ferrell.
You gotta go Days of Thunder.
You're out first or last, Mr. Burns.
Oh, I don't even know this stuff. I'm sure he would know it. My son-in-law would know this stuff. Yeah, okay, all right.
You should tell this to the people who designed the Chicopee curve.
What's that?
You should tell this to the people who designed that curve on 91.
Oh, yeah. Oh, well, they say the speed limit, they lower it, but people don't care. People just don't care. They just keep on going around it anyway. Oh, yeah.
They have like 3 on-ramps going into that curve.
Yeah.
On each side.
Yeah.
It's crazy.
That's crazy. All right, so here we go. Let's derive the formula. I want to do one more proof today again. In a proof mood, you know what I mean? All right, let's derive the formula for the projection of u on v. Well, call this angle theta. And here's what you should realize. This vector, this projection of u on v is some constant times the unit vector in the direction of v. Okay? V divided by its magnitude, this is a unit vector in the direction of v. Now that vector could be something like this. Okay? This right here, let's say, is the unit vector. Okay? That's the unit vector v over its magnitude. Here's what I'm doing. I'm taking a unit vector in the direction of v, and I'm multiplying it by k, where k is the length of this projection. Okay? So k is the magnitude of the projection. Okay? Does that make some sense? I got a unit vector going in the direction of v, but then I multiply by the length of the projection. And what does that do to that unit vector? It stretches it out so it has a magnitude of k. And what will that vector be? That is our projection of u on v. Okay? I'm multiplying by the length of the projection, and I will get the projection itself. Okay? That makes some sense? Maybe, huh? Well, let's do it, and then we'll do some examples, and hopefully it'll make some sense. Okay? Brandon, what do you think?
So projection of U on V is U, but just like as if it were on V, is what you're saying? Like,
Yeah, but, I mean, it's not U, because if you were to just move this, U would be out to here, okay? But imagine a light source here. It would be the shadow of U on V. If you had a light source directly above this as a perpendicular to V, it would be the shadow. I'll tell you what, let me ask you this. Suppose U is perpendicular to V. Then what's the projection of U on V?
would be 0?
0 is correct. There would be no projection at all. Okay? All righty?
Standing right under the sun.
Yes, that's right. At high noon, you get no shadow. You know, we don't get that here. All right, you'd have to be somewhere on the equator to get the sun directly overhead. It doesn't occur anywhere on Earth, but on the equator. Am I right in saying this? I think you have to be on the equator to get the sun directly overhead. Well, there's a 22.5-degree inclination of the Earth. That's why we get our seasons. But
There's the center of the Earth on the center of it. It's not Earth.
see, we never get the sun directly overhead here.
Southern hemisphere. Maybe.
What's that?
Don't you think the southern hemisphere?
Well, here's what happens. Yeah, it depends. If you're at the 22.5 degrees, Tropic of Capricorn, latitude south of the equator, to Tropic of Cancer, 22.5 degrees north latitude, in between those two, they will get the sun directly overhead at certain times of the year. Okay? At the vernal equinox, start of spring, the sun will be directly overhead at 22.5 degrees north latitude on March 20th or so. Directly overhead. I believe this is all true, what I'm saying here. Okay? And then what happens is it travels back down. It's directly over the equator at June 21st. Okay? And then it keeps on going, heading south. It's directly over the Tropic of Capricorn, 22.5 degrees south, on September, we just had this, September 22nd. That's the autumnal equinox. You'd have to look this up.
So plus or minus 22 degrees.
Yes, 22.5 degrees, plus or minus. It never gets directly overhead here because we're at like 45 or 43 degrees north latitude. But between those two, it will get directly overhead at certain times of the year. You'd have to look that all up. Patrick.
I thought it was the equinoxes that it was at the equator. Because wouldn't that make sense? Because if it was summer here, that's when the sun's closest.
Autumnal and a vernal equinox. Yeah, what did I say?
You said the opposite. You said that the equinoxes would be at the Capricorn and Cancer.
Market.
Come on, Burns.
Teddy Market.
Okay, you may be right. I could have said it wrong. I would not be
I
surprised.
wanted to make sure.
Okay.
We'll have to play it back. We have it all recorded.
Oh, that's true. Is there anybody that is good at editing video? Is there anybody?
Very hard.
It could be right. Whatever I said, basically in the spring, it's overhead at 22.5 north, right? In the spring, it's directly overhead at 22.5 north. That's the Tropic of Cancer. You agree with that statement?
Or would that be summer, though? Because
No. What happens is, at June, in the middle of summer, it's directly over the equator.
okay, that is.
Okay?
But he did say it.
I think I said it right, but maybe not. Never know. Okay.
So it's the shadow.
Okay.
Stick with shadows and vectors over here.
The shadow here. All right, let's go. You ready? We're going to do this proof. We want to be able to find that projection of U on V. Given that projection, that vector, is the length of its magnitude, its length, times the unit vector in the direction of V. This length tells you how much to stretch the unit vector so we get the projection that we want. I want to solve for K right now. Liam, go ahead.
So the unit vector, I'm trying to remember.
This is our unit
Like
vector.
your I and j divided by your magnitude to just give you the amount of direction in each.
A unit vector of any vector is, take the vector, it's the vector in that same direction having unit length.
Okay.
Okay? That's what it would be. If you take a vector 5, 0, I, which is 1, 0, is the unit vector in the direction of that vector.
Okay.
Okay, let's do it. You ready? Okay, let's see what we got here. Wow. Working like a dog. Okay, here's our vector v. Here's u. Am I off? Here's what I want to do. Right now, I want to find k, which is the length of this projection. K is equal to the magnitude of the projection of u on v. That's what k is. Okay, the magnitude of that projection. And then what I'm going to do to find the projection, that vector, is to take k times the unit vector in the direction of v, because that'll stretch out that unit vector, so I will have the projection of u on v. That's what I'm going to do. What's k? Well, we have a right triangle. Cosine of that angle is the adjacent side over the hypotenuse, which is the magnitude of u. Okay? K, therefore, is the magnitude of u times the cosine of the angle. But we know what the cosine of that angle is. The cosine of that angle is equal to its dot product over the product of the magnitudes. We just derived that. Okay? Therefore, these cancel. I get k to be the dot product over the magnitude of v. Now, my projection of u on v is equal to, like I said, k times the unit vector in the direction of v. K is this length. We found out what that length is. It's the dot product over the magnitude of v times the unit vector in the direction of v. Wow, these proofs are cool. You can leave it this way, or generally speaking, what you do, you put it this way. Dot product, magnitude of v squared times v. Now, would I expect you to know this thing here? Yeah, I'm going to ask you that. One of the first questions, this test, the next test, first 6 questions or so are on vectors in 2 space. Add them, subtract them, find the magnitude, find a unit vector in a direction, find the projection of one on the other, find the angle between 2 vectors, find this kind of stuff. Just usual stuff, okay? Should be pretty simple, actually. This test, like I said, the first test is usually the worst test. This test is usually the best one because it's pretty simple. Just do the problems. Okay, I just do the homework and then you got the test, all right? Let's do an example. You ready? I'll tell you what, let's do, oh, no, not ready. Okay, not ready. Wait, Eric, who was looking for Eric today? Several people were looking for him. Were you around there? Somebody's looking for Eric?
Oh, this guy.
Yeah.
I was looking for you earlier.
Oh, you were? Okay.
That's all good.
Yeah. I knew somebody was.
I'll sign it.
Okay. Wait, everybody else set? You all set?
Yep.
Okay. Let's do this simple. Let's do a very simple example, just to verify that what we have is reasonable here. Let's take this. Let's take a vector 5, 0, say. And let's take vector u to be 3, 4. And what we want to do is find the projection of u on v. Now, without doing the calculations out, just by using your brains, which are considerable, what is the projection of u on v? 3. It's the vector 3, 0. The length of that projection is 3. The projection itself is a vector that is 3, 0. Okay? You drop the perpendicular down, that's what it's going to be. This vector is going to be. Let's do the little formula that we have. The formula says, to find the projection of u on v, take the dot product, the magnitude of v squared, times v. That's what our formula says. Well, let's see. Dot product of u with v is 15 plus 0 is 15. The magnitude of v is 5. Squared is 25 times v. Okay? Simplify this, divide by 5, divide by 5. We get 3/5 50, which is 3, 0. Okay? How's that? We all set with that? Okay. Good deal. All right. What else are we doing? Not much. What's that?
Categories.
Categories?
Scattergories.
Scattergories. Wow. I haven't played that game in a real long time.
7 Up.
What?
He's calling you out.
7 Up? What does that mean?
I've never. It's been a while. There's a lot of people in this classroom.
We need to
work.
yeah.
Wait.
Let's play a big game of 7 Up.
I don't even know. What is that game?
Everyone puts their heads down, and 7 people come and tap. You get to pick one person, you tap them, they put their hand up, and then at the end you try to guess who picked it.
I don't get it.
That's such a
You have to guess who tapped you. That's
the whole game.
You have
It's
a
big
1 in
person
7
that
chance.
probably, like,
It's math.
hit you.
It's basic math.
Probability, come on.
This is craziness. What a game. All right. I'll tell you what. I'm going to give you a problem to do, because this is what I was doing today. Cosine of the angle, which you have to know, and the projection of one vector on another. And that's about it. So let me give you one example. You guys do it, and we're going to be done. So let's do a little bit more complicated example. I don't know, it's not going to be much, though. Let's take a vector, I don't know. Let's take 6, 4. We'll take my height, and then we'll take another vector in my dreams, you know. Let's take and let's take another vector, let's say 3, 2. And here's what I want. I want the projection of the one vector. Wait, 3, 2 is not going to be there. Let's take 3. What can I make out of this thing?
3, 8.
3, 8. I can make an 8 out of that. 3, 8. Okay, good. Okay, go ahead. Find the projection of one vector on the other. Oh boy, I got to do this now, I guess. Don't even bother to simplify. Well, you can simplify one step, but 3, 8. Oh, that's because the 8 takes it way over there. Okay, I see why now. All right, well, I got an answer. Who's got an answer? All right, hold on. All right, I can wait. All right. What are you guys doing? You guys... Oh, maybe we should do another one, too. Anybody?
50 or 52 times 6,4.
Okay, or 25, 26 times 6, 4. Yeah. Yeah. What were you guys doing? What happened?
Can you do this?
Yeah, let me do it now. Okay, let's do it now. Here's a little formula right here. This is what we need. Okay? So, to do this problem, the projection of U on V, this is U, this is V, okay? Projection of U on V is equal to their dot product. The dot product is 18 plus 32. Okay? That's how you find a dot product. 3 times 6, 18. 8 times 4 is 32. 18 plus 32 is 50. Magnitude of V squared. The magnitude of V is the square root of 36 plus 16, 52. It's the square root of 52. Square that, you get 52. Times V. Well, what you should do is say 25, 26, 6, 4. Okay? You could take a 2 out of here, actually. The best answer would be 25 13ths. Okay? Over 3, 2. Yeah. That would be the best answer. Okay? We better do another one. I don't know what happened there. I'm not sure. Okay, let's do this one.
Would you want us to find the two numbers inside of the actually multiplied curve?
What do you want, Dan?
25, 13 times 3 and then...
Oh, no. When I put it on the test, that's the answer you'll see. Okay? That's the answer you'll see. Just like that. All right, one more. Let's do one more. Let's make sure we're okay on this. This is like a fundamental thing we have to do. All right, let's say U is equal to... let's put V down here somewhere. Let's say V is equal to 3 negative 8. And let's say U is equal to 1 8. And find the projection of U on V. So, and this is what can happen here. The perpendicular from here to here doesn't fall on V itself. It's back here. Okay. This is the projection. And so what you should get is this vector pointing back that way. Okay, that's what you should get when you do this out. Oh.
Nothing cancels out.
What's that?
Nothing cancels out.
I know, it's a pain in the neck. No simplifications, no nothing. But it does illustrate the one thing. You do get a negative number there, which moves the V in the other direction, which is what should happen. Okay. You need more time? Who wants more time? Anybody want more time? Yeah, okay. Do. Okay. Who's got an answer? He is pretty confident in. Go.
Me too.
Oh.
I just wanted to have it.
All right, go ahead.
Negative 61 over 73 times 3 negative 8.
Perfect. Okay. That projection is negative 61 over 73, 3 negative 8. Okay? But you also said, yeah.
Quick question about that. Is there any preference with the negative sign like that? If you had negative 61 over 73, 3 negative 8, if it was like, say, 61 73 minus 3.
Yeah, there's a couple things you could do, but here,
Form for how you want it.
the preference is this retains its integrity.
Okay.
You want to keep V what it is, and you don't want to mess around with these signs. In other words, you could take a negative 1 out, make it 61 73rds, and have a negative 3 8. That's not the thing to do. Leave vector V alone and show that it's a negative number times vector V, which moves it on the other side. So V goes from here out this way, which is what we said had to happen. Yeah, good call. All right, so this is 11 something, 2 maybe? Still 2, I think. 11-2, because it's vectors in 2 space still, probably 11-2, maybe. And then we're going to do vectors in 3 space tomorrow. We'll go to 3 dimensions tomorrow. This is good. It's a big step. We go to 3 dimensions, yeah. Get out of our flat 2-dimensional world and go 3D. This is good stuff. We'll do that tomorrow. All right. See you tomorrow.